Hello everyone, welcome on this video. Today topic is about Newtonian orbits versus orbits in general relativity. So we're going to compare the effective potentials. Let's go. So I'm gonna share my whiteboard. And before the video starts, you can adjust the playback speed if you want to watch this video. So Newtonian orbits versus general relativity. All right. So let's start by the Newton case. So we write Newton. So if we're talking about orbits, Newton or Einstein, orbits always involve that the energy is conserved and the angular momentum is conserved. And we can use those conserved quantities to construct the orbit. So in the Newton case, E is equal to the kinetic energy and plus the potential energy, which is a half of mv squared minus g m m over r, and the angular momentum L is equal to m r squared phi dot. All right. If we now go to polar coordinate, you can write E as 1/2 m of r dot square plus 1/2 r squared phi dot square, and then still minus gmm squared, mm over r. So this is when we go in polar coordinate. And now, if we want to get rid of phi dot and would like to see the angular momentum appear in E, we can just see from there then that phi dot it's equal L over mr squared, and if we plug this in here, we obtain thus that E equal mr dot square over 2, this didn't change, and then L square over 2 mr square minus g m m over r. All right, and this, I'm gonna change color. This is what we call the Newtonian effective potential, UF. And I can put the subscript N for Newton. So we're still in Newton theory. And it's a potential in function of R. All right. So that's how we found that's how we find the potential. And I'm gonna plot it later to compare with the one we're going to find now in general relativity. So now let's look at general relativity. So still orbits imply that energy and angular momentum are conserved. In GR, we will adopt the Schwarzschild metric. So the line element looks like T squared equal minus 1 minus 2m over r dt squared plus 1 minus 2m over r to the minus 1 dr squared plus r squared d omega squared. All right, this is the Schwarzschild line element. It's the only solution to Einstein vacuum equation outside the spherically symmetric distribution of matter. So for example, outside the shell of Earth, so gravity on Earth, gravity in the sky, and gravity in the atmosphere and beyond, it can be described by this Schwarzschild line element. All right. First thing we can say is that an orbit is always somehow in a plane. If this is the sun and this is the orbit of the Earth, an orbit will always be in a plane. This is consequence of mechanics. And so we can choose the equatorial plane, theta equal pi half. So d theta will be 0 and d omega will be 0. This is because d omega, it's r square d theta square. So this we say 0 plus sin theta square d phi square. And sin theta, if theta equal pi over 2, it's 0. And this is d omega square. So d omega square goes to 0 if we take the equatorial plane pi over 2. Okay. So this is the first thing we can do, because orbit, the motion of an orbit is in the plane, orbit is plane. All right, next thing we can see from this line element also is that it does not depend on the time coordinate t and the phi coordinate, the angle coordinate phi. So we know that we have two Killing vector fields related to these symmetries. The first one is the time translational symmetry. This one related to the fact that the line element does not depend on t. And the second one is related to phi, is this one. And the way to, because an orbit is a geodesic, it's a free fall. An orbit is a geodesic. We can find the conserved quantity along a geodesic, so along this orbit, in the following manner. So this will give the energy per unit mass, and this will give the angular momentum per unit mass. And as a reminder, the forward velocity of an observer, u alpha, will be dt d tau, dr d tau, d theta d tau, and finally d phi d tau. All right. So this will only take the 0 component. Because we have only a 0 component here. So this will only be equal to minus G00. I don't know the name of this Greek letter, sorry, 0 and U0. That's the inner product, which will give us 1 minus 2m over r dt over d tau. And this, because it has only a third component, theta, it will give us G3 3 theta 3 U3, which if we compute give R square sin square theta T phi d tau. All right. So this is how we can find the conserved quantity on our orbit. And now using the condition on the velocity, namely that u square should be -1. Right, so if we compute this inner product, knowing that it should be equal to -1, and if we say that dt d tau, it's E divided by 1 minus 2m over r, and we say that d phi d tau, it's L divided by r squared sin square over theta. This you can read it from here. Then we find the following energy, E squared minus 1 over 2, that we are claiming is the expression to compare with Newton energy. And I will explain why. And so this is equal to half of dr d tau. We don't have an expression for dr d tau in terms of the conserved quantity, so we have to keep it this way. But then plus 1/2 1 minus 2m over r 1 plus L squared over r squared minus 1. Let me check the -1. I'm not sure about -1. Yes, -1. Okay. All right. So this is the expression we claim to compare with Newton energy, and this is what we call, I should put it also in blue. This is what we call the effective potential in GR. So now we can compare. We found the expression for the energy in Newton theory and the expression for energy in GR theory, and I claim that these two last expressions are the one that we can compare. So let's check if we can compare them. How do we do that? So general relativity is accounting for the rest energy, which Newton is not. So if we want to compare an energy in GR with Newton, we have to introduce E Newton, which would be the total energy, sorry, which will be the total energy in mc squared minus the rest energy, and then we can compare it. So minus mc squared, and then it becomes Newtonian if we subtract the rest energy. Okay, this gives us E equal 1 plus the famous, not famous at all, but 1 plus E n mc squared. I'm sorry, it's slower and slower because my computer is dying and dying more and more. 1 plus E n mc squared. And this, if we go in the non-relativistic limit, so the Newton case, because Newton is never taking account of luminic speed, we find that E squared minus 1 over 2 in the non-relativistic case is equal to En over mc squared. Thus, E squared minus 1 over 2 is the expression to compare with Newton energy. Alright, so that's why I claim that we can compare it with Newton energy. Okay, and one last thing before I plot both potential is that VF, if now I develop the terms here of VF, it's equal to minus m over r plus L square over R square minus M phi square over R3. Okay. And if I want to go back to here, I'm in Geometra's unit, but if I want to go back to SI unit, then I will replace, then M becomes mg over c square. The big M here, I should multiply by g and divide by c square if I want to be in SI unit. L would be the normal capital L for angular momentum divided by mc. And I should multiply everything by mc square because here we have to get rid of this mc square. So I should multiply everything by mc square and then I obtain the effective potential that I can compare with Newton effective potential. And this is exactly, if you do the algebra, which I won't because my computer is dying, this is exactly equal to Newton effective potential plus a new term, actually it's a minus, m g L square over c square m R3. So the effective potential we find in GR is equal to Newton effective potential minus mg L square over c square m R3. We see that it's an attractive term because of the minus in front. It will dominate for small r because the Newton effective potential, there is only one term divided by r and one term divided by r squared. But here we divide by R3. So for small r, it will dominate. But for big R, we see that general relativity goes back to Newton theory. For big R, Newton is totally accurate. All right, and so now I guess it's time to draw the plot, and we are soon finished with this video. Okay. Okay, so Newton plot look like this. So energy axis and the radius here r, and effective potential U looks like this. All right, so this is U effective. This goes to infinity here, and this goes to infinity here. This is U effective of R. And we see that, of course, it's for angular momentum different than 0. Otherwise, it would just be a radial fall. But here we're talking about orbit, so we have some angular momentum that is conserved. So here we have circular orbits. Here we have perfect ellipse, elliptical orbits. Here we have parabolas and hyperbolas, which are unbound orbits, and circular and elliptical are bound orbits. And we see that we can never reach r equals 0 if we have some angular momentum. R equals 0 is here, and we can never reach it. The potential is doing like a barrier to infinity. So in Newton, the only way to reach r equals 0, if you have some, it is to have no angular momentum. If you have some angular momentum, we see because of the shape of this effective potential that you will not reach r equals 0. In general relativity, it's not very different, it's a bit different. Different enough, at least, to consider black hole, for example. Sorry. Hmm. This is my energy axis. Radial axis. And the potential, if we plot it, look like this. All right, so this is V effective as a function of R. All right, and the new part is everything here. It's because of the new term that we have here. We said that V effective was U effective minus plus this new term, this new attractive term, and this is what creates everything I've put in red here. So what's new is that here, sorry, I wrote E, but it's E squared minus 1 over 2. So if you have high enough energy per unit mass, even though you have angular momentum, you can reach r equals 0. We see here that we can reach r equals 0, even if we have angular momentum, which was not possible in Newton. We have circular orbits here, but also here, except that here, if you move a bit left or right, you will come back to it. So we say that it's stable circular orbits, while here it's unstable circular orbits. The ellipses no longer close. So this is why the orbits of Mercury in the solar system are precessing, and actually every elliptical orbits are always at least a slightly bit precessing. So it means that if this is the Sun and this is Mercury orbit, it never comes back exactly at the same point, and it will precess. This is because the ellipse is not closing here. If we want the ellipse to close, we will need a potential like this. But because of this part here, it does not close. We still have, for E equals 0, we still can reach R infinity. So parabolas, here we have hyperbolas. And that's mostly it. So far away for big R, we go back to Newton's theory. But for small R enough, we can observe unstable circular orbits or precession in the elliptical orbit. And here is the radius of the event horizon. It's r equal 2m, Schwarzschild event horizon of a black hole. And yes, that's it for today. Thank you for watching.